Hi everyone, welcome to the teaser video of Fed-CASQ, a way to make quantized federated learning fair to the underrepresented classes. I will start with the motivation behind this work, then the key idea of Fed-CASQ, and end with the results on accuracy and resource efficiency. So this work is a collaboration across UMBC, IIT Jodhpur, University of Virginia and Singapore Management University with support from UNR, the US Army grants and NSF. Now let's jump straight into the motivation. So federated learning is a well-established decentralized training approach to deploy FL on pervasive IoT devices. Quantization to lower bits is a major compression choice to save compute and communication. But in one of our such efforts, we observed that quantization amplifies class-wise accuracy gap. Specifically, it tends to hurt the low accuracy or undersampled classes disproportionately. So the goal here is that if we can minimize the minority class accuracy gap in quantized FL while staying practical for heterogeneous edge devices, that means the solution must be both resource and class aware. Let's dive into a little detail of our problem setting backed by some compelling empirical evidence. In the leftmost plot, as you can see, with ResNet 18 on imbalanced CIFAR-10's dataset, as the imbalance ratio grows, vanilla FL already drops on the tail classes, and then after applying in-stage quantization adds another 10% drop. Even after adding a sample ratio aware loss, it still can't match the Fed average full precision behavior. The TSNE plots to the right give an intuition to this scenario. After applying quantization, the minority class features overlap more with each other, so the separation degrades. So this is exactly the gap what we are trying to minimize. Here we list the key contributions of Fed-CASQ. First, we introduce a framework that preserves minority class accuracy under quantized FL by selectively scaling a small set of important filters. Second, we use explainability concept, layer-wise relevance propagation, combined with KL divergence to decide which filters matter most for low-performing classes. Third, we reduce communication overhead with a compact sparse representation of the selected filters. Finally, on the server side, we use a customized aggregation strategy to improve stability and reduce rounds to converge. Now I'll walk you through the workflow of Fed-CASQ. To begin, we evaluate each participating device's available memory, signal strength, and bandwidth, and we compute a resource score. Based on that score, we assign a suitable bit width per client. Resource constrained devices quantize more aggressively while stronger devices afford higher precision. This lets us handle heterogeneity without forcing one fixed quantization level for everyone. Next is a local training block. As soon as the client receives the initial weights, it trains locally, but we add an LRP driven step to generate class-wise relevance maps. Those relevance signals help us identify filters that are important for the low performing or minority classes, and also identify filters that are good candidates for sparsification. The key idea here is we don't scale everything, we scale only what matters for the minority classes and sparsification. After local training, the client sends the model updates plus meta information, which are the indices, values, and dimensions of the sparsified filters. On the server side, we reconstruct the original tensor shapes from the compact representation, then do aggregation. We use a cosine similarity check between successive global models as a lightweight guard against catastrophic forgetting in noisy quantized updates. Now let me zoom in one of the core mechanisms of this Fed-CASQ framework, which is LRP-driven filter selection. So as the first step, in each client for each filter, we generate class-wise relevance maps using LRP. Intuitively, these maps tell us which filters contribute the most to each class decision. We compute these maps locally, so the server never needs raw data. Then we aggregate relevance maps per class, basically averaging across samples to get a stable class level signal. Then we compute KL divergence across the class-wise relevance distributions. Higher divergence tells us the filter behaves very differently across classes, which is what we want when looking for filters that are specifically informative for a minority class. To reduce computational overhead, we don't do this across every class. Instead, we take the two top performing classes and the least performing class within each client, then run the relevance comparison on this subset. For the relevance decision, we formulate hypothesis testing based on p-values, and we derive a shifted logistic function to mark a filter as minority relevant and a candidate for scaling. In this slide, we can see a clear difference between relevant filters, which show concentrated class-specific patterns, and sparse or less useful filters, which can be pruned or compressed with little impact. So in Fed-CASQ, we use the relevant set of filters to scale, and we hope to recover minority class accuracy, and we use the sparse set to reduce the uplink overload. Now, before jumping into the results, let me quickly summarize the experimental and evaluation setup. So for this work, we used 4 baseline datasets, 7 relevant baseline methods to compare with, and we deployed our method on 7 heterogeneous devices. Also, we evaluated Fed-CASQ from 4 different point of views. First, we did baseline analysis and also deployed FL on heterogeneous devices and did resource efficiency analysis. Then we did sensitivity analysis, and lastly we carried out a detailed ablation study. So here we can see the performance of Fed-CASQ compared to different baselines. So the key takeaway in here is that Fed-CASQ closes most of the gap between quantized and full precision training for the minority classes, outperforms strong baselines under severe imbalance, and stays competitive on the majority classes. Specifically, at an extreme imbalance ratio of 100, Fed-CASQ reaches about 52% of minority class accuracy, surpassing methods like Balance-FL and RAM-Fed, while still keeping majority class accuracy high, around 91%. Here we present the resource efficiency comparison across baseline methods. After analyzing the results, we found threefold advantages. With Fed-CASQ, we achieved faster convergence, lower energy and memory overhead, and lastly reduced uplink overhead. In this slide, we try to break down the resource efficiency analysis of Fed-CASQ by device type. From these results, we could validate the impact of Fed-CASQ through the following 2 points. First, devices with lower computational capability and RAM take longer per local epoch, but they can still be energy efficient. Secondly, uplink overhead and energy consumption also show the impact of appropriate bit selection method of Fed-CASQ. Now, here we want to know how Fed-CASQ performs under different sensitivity analysis. So we show 2 sets of experiments in here, like varying number of clients and varying dataset. So as you can see, Fed-CASQ can successfully retain the percentage of scaled filters with increasing client numbers, although it shows an inverse relation in case of global and minority class performance with increase of number of clients. So the reason can be the diverse set of samples enables richer aggregation, but data heterogeneity and variation in filter selection negatively impacts minority classes. Also, after looking at the plots of varying dataset, you can see the convergence results after convergence results of Fed-CASQ varying different dataset choices. Here we can see the other 2 sets of sensitivity analysis. So in the model diversity part, as you can see, Fed-CASQ can be applied to convolutional transformers. Also, Fed-CASQ actually improves the majority class accuracy along with the minority class, showing the fairness aspect of it. So the ablation study answers the impact of each component used in Fed-CASQ. So adaptive quantization has a significant impact in reducing uplink communication. Scaling has the largest impact on accuracy, boosting minority class performance by roughly 10 to 20%. Custom aggregation contributes to the additional minority class improvement, and sparsification gives a further few percent reduction in uplink. So to wrap up, we tackle the minority class degradation in quantized FL under data imbalance. Fed-CASQ combines adaptive quantization with an LRP guided filter selection approach that scales only what minority classes need. Also, we validated across multiple imbalanced scenarios, model families, and also on real heterogeneous edge devices. Thank you for your time to listen to this presentation.